It's one of life's little ironies that it is not new, cutting-edge technology that is advancing our understanding most at the edge of our solar system, but an old machine. It has an onboard computer with less memory than the one inside your car's key fob. To this day, it is still using 8-track magnetic tape from the 1970s, which makes it older than many of you sitting here watching this. Such is the conundrum of deep space exploration, where vast distances and extremely long travel times can mean that technology is antiquated by the time it has reached the most ambitious targets. But it's true, that record-setting spacecraft is, of course, the nearly 45-year-old Voyager 1 probe. Along with its twin, Voyager 2, it became the first human-made object to reach interstellar space. It takes over 21 hours for NASA to send and receive radio signals with Voyager 1, covering a distance of 23 billion kilometers, versus about 20 minutes to send a radio signal to Mars. And while it's astonishing to think that we can still communicate with a 3.7 meter antenna over such an immense distance, it's even more incredible when you consider that the probes are relying on technology that would look more at home in a museum than NASA's Jet Propulsion Laboratory. For such technology to have done so well, lasting so long, it must have been special. So, what secrets lie inside? How were Voyager's engineers able to build spacecraft capable of operating continuously for such a long time, beating all records? I'm Alex McColgan, and you're listening to the Astrum podcast. Join me today as we explore the technology of the Voyager probes and learn how a series of shrewd engineering choices paved the way for the most ambitious and stunningly successful mission in the history of space exploration. Although Voyagers 1 and 2 were initially built for a 5-year mission to explore Jupiter and Saturn and their larger moons, their team of forward-thinking scientists and engineers made a number of design choices that enabled the probes to hold up over a much longer journey. To recap, after completing all of its initial objectives on Jupiter and Saturn, the Voyager 2 mission team added flybys of Uranus and Neptune. Once these two were completed, NASA announced the start of the even more ambitious Voyager interstellar mission, with the purpose of exploring the outer limits of the Sun's sphere of influence and beyond. This final journey would take both probes off the ecliptic to unexplored parts of the solar system, such as the termination shock and the denser and hotter heliosheath, before finally crossing the heliopause into interstellar space. Let's start with one of the most consequential decisions: the energy source. Each probe is equipped with a long-lasting radioisotope thermoelectric generator, which converts heat from the decaying plutonium-238 isotope into electric power. These generators were capable of producing 157 watts of electrical power upon takeoff, about enough to power a laptop and maybe charge a mobile phone too. This might not sound like much, but was more than Voyager needed. While a radioisotope generator meant that power production was in constant decline, it would halve in strength every 87.7 years, it would still be enough power to keep the essentials on the probes running until at least 2025. This long-term energy capacity was no accident. You see, when the Voyagers launched in 1977, NASA faced a unique opportunity. The planets would soon be in a 1 in 176 year alignment that had last occurred during Napoleon's first reign. This rare alignment would not only allow the Voyagers to visit Neptune and Uranus with minimal course adjustment, but also give the probes a gravity assist from each of the 4 outer giants they visited, thereby increasing their effective velocity beyond what they could get from their own rocket propulsion. However, this narrow window gave NASA a strict deadline. There wasn't enough time to plan follow-up missions, and the United States Congress wouldn't earmark enough funding for a longer expedition, like the grand tour NASA first proposed. So, what did Voyager's team do? They devised a series of engineering feats to optimize the probes for a potentially longer mission, and fervently hoped that the funding would follow. Each of the Voyager probes is equipped with 11 scientific instruments. Most of them have redundancies in case of machine failure, which can be toggled on and off to conserve power. To adjust course and orientation, the probes are equipped with gyroscopes for stabilization, referencing instruments, and 16 hydrazine thrusters, including 8 backups. Backups, and good backups at that, were key to the Voyager probe's longevity. They proved to be vital, as Voyager 2's main thrusters stopped working after 37 years. Its backup thrusters had to engage after 4 decades of idleness. And guess what? They worked perfectly, highlighting the excellent engineering that went into them. The Voyagers also have custom-built onboard computers, which are antiquated by today's standards, but were cutting edge in 1977. The probe's wide-angle and narrow-angle lens cameras are controlled by a computer command subsystem, which has fixed programs like fault detection and correction routines. Another key to its success lay in its computers. Each probe had a computer called the Attitude and Articulation Control Subsystem. And no, it doesn't scold the Voyagers when they get sassy. Attitude refers to probes' orientations with respect to the Earth, without which their high-gain antennae would be unable to send or receive signals from NASA's Deep Space Network. This is very important, as the probe's transmitters only have the wattage of a refrigerator light bulb, and at such immense distances, their radio signals become barely detectable whispers. To communicate with the Voyager team and vice versa, the probe's antennae must be facing the Earth, and the Deep Space Network must in turn know exactly where they are. Otherwise, they would be lost, like a needle in a 287 billion kilometer haystack. Each Voyager spacecraft has a 3.7 meter antenna for real-time transmission and an 8-track digital tape recorder capable of buffering 536 megabits for future transmission, enough to store 100 photographs. While this was still a huge step up from the earlier Pioneer probes, which had no onboard data storage, it's still a fraction of what the smartphone in your pocket can store today. Despite these limitations, the DTRs were built to last. Odetics, which manufactured them, claimed that their DTRs could process over 4,000 kilometers of tape without taking visible wear and tear. They had to withstand the harshest environments imaginable and undergo rigors that had never before been tested. Yet the Voyager DTRs performed without data loss or machine failure, and Voyager 1's DTR is still working to this day, although Voyager 2's DTR was turned off in 2007 to conserve power. Not bad for machines 12 years older than the World Wide Web. Durability was a chief concern during Voyager's planning. There are many unknowns in a mission of this magnitude. To get to Jupiter, both Voyagers would have to pass through the asteroid belt. Scientists once believed that this region would shred apart any spacecraft that tried to pass through it. However, Pioneers 10 and 11 had previously been able to pass through the asteroid belt, which emboldened Voyager's team to repeat the stunt. However, failure would have meant disaster before the probes had even reached their first target. Luckily, both probes made it through the asteroid belt unscathed, and we now know that it is mostly empty space thanks to them. Even with all these successes, and with the probes performing far better than their engineers could possibly have hoped for, as the two spacecraft traveled through the vastness between the planets, there was still at least one more hurdle to cross. What would happen to the probes in the extremely cold temperatures of interstellar space? NASA installed multiple heaters to keep the machinery operational. Nonetheless, as the probe's power waned, NASA had to turn off some of their heaters to conserve energy. When the cosmic ray detector's heater was turned off 2 years ago, its temperature plummeted by 70 degrees Celsius. Needless to say, sending a repair team 23 billion kilometers into space isn't an option. So everyone thought the instrument would break, but it continued to run smoothly. The fact that the probes have operated so well for 45 years is a testament to their resilience and engineering. But for any mission as long and ambitious, there are always things no one can predict. Not everything on the Voyager missions has worked perfectly. Voyager's team learned this recently when Voyager 1 started sending mysterious scrambled signals. I talk about this in more depth in another of my videos, which you should check out by the way. But at a June 2022 meeting of the National Academics of Science, Engineering and Medicine, NASA announced that Voyager 1's attitude, articulation and control system had been spitting back strange sequences, like rows of zeros that appeared to be nonsense. While the probe itself was operating normally, we knew its speed and distance, and it was still responding to and taking commands, its telemetry data was a complete scramble. In other words, Voyager 1 had no idea where it was. Sadly, this turned out to be a sign of a failing computer, and although scientists were able to find a workaround by moving over to a backup, there will come a day when there are no backups left. Still, we have a lot to be thankful for. Voyager 1 has traveled farther than any other human-made object, including its twin, Voyager 2. Its technology, although rudimentary by today's standards, has really shown what can be done with even simple tools. Its discoveries have been a monumental step forward in our understanding of our solar system. When we do inevitably say goodbye to this erstwhile friend and its twin, Voyager 2, it will be time to apply the engineering lessons of the past to try and recreate the magic with a successor. Already, there is a proposal from Johns Hopkins Applied Physics Laboratory for an interstellar probe that would launch in 2036 and reach interstellar space in just 15 years. Of course, even if it does, by the time it is reporting back from the fringes of interstellar space, it too will be a thing of the past. But there is something inspiring in that. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast on the incredible engineering choices behind Voyager 1 and 2. If you like what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.